Graphing was in section 4.6, but so is modeling exponential data. So let's do that. We're going to model growth and decay scenarios, and of course we're going to interpret our answers because that's what we do. Bacteria. All right, lots of growth. And bacteria is a very common example of growth, but I need you to know there are more examples of growth, and bacteria is just like the easiest one to pick on. But reproduction in general, I mean, you could even look at the population of humans on this planet. Anyway, suppose there are 3 million bacteria at 11 o'clock today, and that one bacterium divides into 2 bacteria every hour. Ooh, that's interesting. Fill in the table. So it's 11 o'clock, so just so that I'm crystal clear, it's 11 and every hour. So 1 hour later it is noon, and then 2 hours later it's 1 p.m. and 3 hours later it is 2 p.m. Okay, just to keep track of time. Number of bacteria. We started with 1. 1 hour later there are 2 because that 1 split into 2. Now there are 2 of them. Each one of these split into 2. So now one of them split into 2 and the other one split into 2. So now there are 4. And now, oh my gosh, this reminds me of the COVID model. And there's a video that you can find that explains this and how it's happening in our world right now. Anyway, so there's another thing that actually is exponential growth, is like the spreading of a rumor and the spreading of a virus and things like that. Anyway, except there's a cap because there's only so many of us. Anyway, so each one of these is now splitting into 2. So 4 of them each become 2 of them. So now there are 8. Got it. Okay. So far, so good. Is this model linear, quadratic, or exponential? Well, I see the pattern is double, double, double. That means it's exponential. How can you tell? Constant multiplier of times 2. Got it. It's the pattern, man. Write an equation that models the situation. Clearly indicate what your variables are. Okay, so bacteria, I'll call it B for bacteria, is the initial amount. So at time 0, at T0 countdown, no, I'm just kidding. At time 0, which is 11 a.m., there was 1. So the initial amount, okay, so just to write down so I can remember this model, constant multiplier to the x. Oh, but whatever. Bacteria equals, okay, 1. The constant multiplier is 2 because it's doubling each time. And I'm going to call it H for hours to the H. So B equals number of bacteria alive. And H equals number of hours past 11 a.m. Got it. Wrote the model. Check. And predict the number of bacteria that will be on the surface at 11 a.m. the following day. Oh, that's 24 hours later. So H equals 24. Assuming that no one comes and cleans that surface and that there are no new bacteria are put onto the surface, right? Like nobody puts a slice of dirty bologna on there, maybe introducing some new contamination. And that, I mean, like, what if this is just a desk, like a kid's desk, and it just didn't get wiped down, you know what I mean? Which happens all the time. Totally normal and natural to not wipe every surface clean all the time. Like, what if it's even the wall? If H is 24, then the number of bacteria is 2 to the 24th. I don't know what that is. That is a calculator's business. So I go 2, and then don't forget that this caret is exponent button. 2, you can't read that because it's too shiny. 2 to the 24th. Whoa. Huh. Okay, what do we got here? 16,777,216 bacteria. Ooh, that's a lot of reproduction. Dang. Okay. Well, now let's look at this caffeine business, because we talked about this in an example in a previous note. But I think it's a different, is it a different data set? I'm not sure, but nonetheless, we should model this. So here's some data, and let's go ahead and see how much is being burnt off in our system, or absorbed and used and then, you know, excreted. So use a calculator to create an exponential model. Ooh. Okay, so here we go. Ooh, we have to make a couple decisions. Darn it. My first decision needs to be that this is independent. And this is my explanatory variable. So I'm actually going to put this into list 1, and this is going to be my explanatory variable, also known as x's. But I'm not going to call it x's. I'm going to call it, ooh, it's hours again. I'm going to go with h for hours again. And the caffeine amount in the bloodstream, that is our response. In the word response, the S comes before the P. Response. Got it. And that's the Y, but I'm not going to call it that. I'm going to call it C for caffeine. And I'm going to put this into L2. Okay. Well, lucky for you, you don't have to watch me type those all in. I went to stat, and then I went into edit, and I put all of those hours into list 1, and I put all of that, milligrams of caffeine into list 2. So here it is, and it says we need it to create an exponential model. So then we go to stat, calculate, and now we don't want a linear regression or a quadratic or a cubic or a quartic or another linear regression or a natural log. Oh man, where is it? Oh, there it is. So you have to keep scrolling down until 0, and it's called XPreg. It has nothing to do with pregnancy. Okay? I hear you, college students. Don't be scared. This has nothing to do with pregnancy. It's exponential regression. So, but if you need someone to talk to, definitely reach out. Exponential regression. I'm going to hit enter. No, not list 5. I want second L1 for list 1 and L2 for list 2, because we made these decisions about explanatory, time, and responding caffeine amount. Compute. Got it. So the initial amount is about 80.23, and the constant multiplier is about 0.89. I'm going to round that too. And it's a pretty close fit. It's a really good fit. It's decaying, so it's negative, but 99%, that's strong. Okay, here we go. So, got it. Use your calculator. Clearly indicate what the variables represent. Yes. So, caffeine is approximately, oopsie, that's an 80.2 with a constant multiplier of 0.89 raised to the number of hours that pass. Okay, so you start with 80.2 milligrams. Okay, I see that that's a little bit off, but sure, it's a model. And you have, what is this as a percent? 89% of it is retained each hour. So this is just a different body than the previous example we saw. Clearly indicate, well, C equals milligrams of caffeine in your system. Right? So it'd be the same if you were drinking Monsters and stuff. H, hours after intake. Okay, I think that makes a lot of sense here. So when I think about how people deliver caffeine to their system, a lot of people just drink coffee, like me. And but many people don't like the taste of coffee, but still have a lot of caffeine in, say, chocolate. And then some people have a lot of caffeine through actual pills like Aleve. And others, while others drink Monster and whatnot. So just FYI, a lot of people drink caffeine. Might want to, not get too hooked. What does A represent in this situation? So know that A in the model, so just to make sure we understand what this is asking, the calculator said this. Whoa, too bright. Oh, it just cleared it. Calculator, calculate the exponential regression. A times B to the X. Okay, so everybody kind of goes with this A times B to the X thing. So this A is 80.2 in this situation. So what does A represent? The initial amount of caffeine in the bloodstream was about 80.2 milligrams. Yeah, that's what the initial amount meant. So this 80.2, initially there was 80.2 milligrams. What does B represent? Okay, well, if you say the constant multiplier, nobody's going to understand what that means. And so I think it's better said that, I'm going to say this two different ways. First, each hour makes or has, so each hour has 89% left from the previous hour. Has 89% of the caffeine left from the previous hour. So you know that previous hour, take 89% of that, and now you know how much is still in your bloodstream. But I kind of like this too. So a separate interpretation of this could be that there was 11% of it lost every hour. So 11% of the caffeine is metabolized and gone out of the bloodstream each hour. Yeah. Because if only 89% of it is remaining, then that means 11% of it went bye-bye, got filtered, got expended, like burned into energy. It's gone. It's toast. Predict how much caffeine will be left in a person's bloodstream after 14 hours. Oh, okay. Well, that means H equals 14. And so we would take our model, here it is, and we would put 14 for the H. So C is approximately 80.2 times 89%, 14 times. Let's see how much that is with my handy calculator. 80.2 times 0.89 carat raised to the 14th power. That is approximately 15.7 milligrams. So predict how much will be left 14 hours later. About 15.7 milligrams. Didn't really completely go away, but it's on its way out. Half-life. Okay, so let's jot down what this word means. A half-life is how long it takes for only half of it to decay to half of what it started as. So the time it takes for an amount to exponentially decay to half of what it started as. Okay, so when I think about the half-life here, it would be asking the question, how long did it take for this 80 milligrams to burn off to being 40 milligrams, because that's half of 80. And the answer is about 6, a little more than 6 hours. Yeah? So that would be the half-life. It would be a little more than 6 hours in this scenario. In the next example, we're going to look at money. Money, caffeine, bacteria, all of it.